Solving systems of 2 and 3 variables. Welcome, everyone. In our previous lessons, we spent quite a bit of time establishing the theoretical foundation of the matrix method, looking at how matrices behave and what they represent. Today, we are moving from theory into practice. Our core objective is to learn how to actually solve a system of linear equations by transforming them into a single matrix equation, where a times x equals b, and then isolating our variable matrix, x, using the formula x equals a inverse times b. Now, you'll notice that the complexity of this process changes depending on the dimension of our coefficient matrix. If the matrix is small, the steps are quick. If it's larger, the process becomes much more involved. To help you navigate this tutorial will serve as a practical, step-by-step guide. We will start with the simpler case of solving systems involving 2 variables, using 2x2 matrices, and then we will progress to the more rigorous method for solving systems with 3 variables, using 3x3 matrices. Let's get started. Solving systems of 2 variables, $2 times $2. Imagine we have a system of 2 linear equations with 2 variables, x and y. We can write these out in their standard algebraic form, where a sub 1 times x plus a sub 2 times y equals b sub 1. And then, a sub 2 times x plus a sub 2 a y equals b sub 2. Now, here is the good news. When we are dealing with a 2x2 matrix, the computational process is much more streamlined. Unlike the more complex 3x3 method we will see later in this tutorial, the inverse of a 2x2 matrix can be found using a very simple shortcut. Let's break this down into 4 clear steps. Step 1. Represent the system in matrix form. We need to pull the coefficients out of our equations to identify our matrix A, which consists of a sub 1, a sub 2, a sub 2, and a sub 2. Our variable matrix x will contain our unknowns, x and y. Finally, our constant matrix b will hold our values b sub 1 and b sub 2. Step 2. Calculate the determinant. We find the determinant of A, denoted as the absolute value of A, by multiplying a sub 1 by a sub 2, and then subtracting the product of a sub 2 and a sub 2. It is crucial to check this value. If the determinant is not equal to 0, we know a unique solution exists. Step 3. Find the inverse of A, which we write as a inverse. For a 2x2 matrix, you don't need a long process. You simply take 1 divided by the determinant and multiply it by a new matrix. To create this new matrix, you just swap the elements on the main diagonal, that's a sub 1 and a sub 2, and change the signs of the off-diagonal elements, which are a sub 2 and a sub 2. Step 4. Finally, solve for x. To find our values for x and y, we simply multiply the inverse matrix, A inverse, by our constant matrix, b. This gives us x equals A inverse times b. Now that we have established the theoretical foundation in the previous slide, let's dive into the practical application, starting with the simplest case, solving a system of 2 variables. Once we master this shortcut, we can apply it to real-world problems, like the cost analysis example coming up next. Real-world example, cost analysis. Imagine you are looking at a simple shopping scenario. One student buys 2 notebooks and 3 pens for $13, while another student buys 1 notebook and 2 pens for $8. Our goal is to find the individual cost of 1 notebook, which we will call x, and 1 pen, which we will call y. To solve this, we follow a clear, step-by-step process. First, we need to formulate our equations. Based on the scenario, our first equation is 2x plus 3y equals 13, and our second equation is 1x plus 2y equals 8. Second, we translate these equations into a matrix representation, just as we discussed in the introduction. We define our coefficient matrix A as a 2x2 matrix with 2, 3 in the first row and 1, 2 in the second row. Our variable matrix x contains our unknowns, x and y, and our constant matrix b contains our totals, 13 and 8. Third, we calculate the determinant of matrix A. We multiply the elements of the main diagonal, which is 2 times 2, and subtract the product of the off-diagonal elements, which is 3 times 1. This gives us 4 minus 3, resulting in a determinant of 1. Since this is not 0, we know a unique solution exists. Fourth, we find the inverse of matrix A using the shortcut from the previous slide. We swap the elements on the main diagonal and change the signs of the other two elements. Since our determinant is 1, the inverse matrix is simply 2, -3 in the first row and -1, 2 in the second row. Finally, we calculate x by multiplying the inverse matrix A by matrix B. We multiply the first row of our inverse by the column in matrix B, which is 2 times 13 plus -3 times 8, giving us 26 minus 24, which equals 2. Then, we multiply the second row by the column in matrix B, which is -1 times 13 plus 2 times 8, giving us -13 plus 16, which equals 3. Looking at our resulting matrix X, we can clearly see the solution. The cost of one notebook is $2, and the cost of one pen is $3. Now that we have covered the theoretical shortcut for 2x2 matrices in the previous slide, let's put that theory into practice with a real-world scenario. This method is much more efficient than substitution when dealing with larger systems, which we will explore in the next slide when we move into 3-variable equations. Solving systems of 3 variables, $3 times 3. Now let's step up the complexity. Up until now, we've been looking at 2-variable systems, which we saw in the previous slide were quite straightforward because of that handy shortcut for the inverse. However, when we move to a system of 3 linear equations with variables x, y, and z, we can no longer rely on a simple swap. We need a much more rigorous, step-by-step approach. Let's walk through the computational process together. Step 1. First, we must represent our system in matrix form. This means identifying our coefficient matrix, which we'll call A, a 3x3 matrix. Then, we define our variable matrix X, which is a 3x1 matrix, and our constant matrix B, which is also a 3x1 matrix. Step 2. Next, we need to calculate the determinant of matrix A, denoted as the vertical bars surrounding A. To find this value, you can expand along any row or column, though I usually recommend starting with the first row to keep things organized. Step 3. This is where the work increases. We need to find the matrix of cofactors. For every single element in matrix A, you'll calculate its cofactor, which we call C sub I. J. To do this, you use the formula -1 raised to the power of I plus j, multiplied by the minor, m sub I. J. The minor is simply the determinant of the 2x2 matrix that remains after you delete the row and column belonging to that specific element. Step 4. Once you have your matrix of cofactors, we need to find the adjoint of A. Written as A, the adjoint is simply the transpose of your cofactor matrix. This means you'll switch your rows and columns around. Step 5. Now we can finally find the inverse of A, which is a inverse. You calculate this by taking 1 divided by the determinant of A and multiplying that scalar by the adjoint of A. Step 6. Finally, we reach the goal. To solve for our variables in matrix X, we use the same fundamental formula we've used all lesson. X equals A inverse multiplied by B. It looks like a lot of steps, I know, but in the next slide, we are going to apply this exact process to a real-world factory production scenario to see how it all comes together. Real-world example, resource allocation. Now, let's apply the rigorous process we just discussed in the previous slide to a real-world scenario. Imagine a factory that produces 3 different products, which we will call X, Y, and Z, using 3 different machines. We are given the specific number of hours required for each product on each machine, as well as the total available hours for each machine. Our objective is to determine the exact quantity of each product. To begin our step-by-step solution, we must first formulate our equations. Based on the machine requirements, we can write x plus y plus z equals 6, 2x minus y plus z equals 3, and x plus 2y minus z equals 2. Next, we represent this system in the matrix form we have been studying. X equals B here Matrix A is our 3x3 coefficient matrix, X is our column matrix of variables, and B is our column matrix of the total available hours. Now, we move to the calculation phase. First, we find the determinant of matrix A by expanding along the first row. We calculate 1 times the determinant of the remaining 2x2 matrix, minus 1 times the next 2x2 determinant, plus 1 times the final 2x2 determinant. After performing the arithmetic, we find that the determinant of A equals 7. The next step is the most intensive, finding the matrix of cofactors. We must calculate a cofactor for every single element in the matrix. For instance, the cofactor for the first element, C11, is -1 and C12 is 3. We continue this process for all 9 elements, carefully applying the alternating sign pattern. This includes calculating values like C22, which is -2, and C33, which is -3. Once we have all our cofactors, we find the adjoint of A. This is done by taking the transpose of our cofactor matrix. Essentially, we switch the rows and the columns. This gives us our adjoint matrix. Finally, we solve for our variables using the formula. X equals 1 over the determinant of A, multiplied by the adjoint of A, multiplied by matrix B. We multiply the adjoint matrix by matrix B, which involves calculating the dot product for each row. This results in a new matrix where the elements are 7, 14, and 21. When we divide each of these by our determinant, which is 7, we get our final values. X equals 1, Y equals 2, and Z equals 3. So, the final result tells us the factory should produce 1 unit of product X, 2 units of product Y, and 3 units of product Z. It is a long process, but very systematic. However, as we will see in the next slide, there are several critical areas where a small mistake can lead to an incorrect answer. Common mistakes to avoid. Now that we have worked through the step-by-step processes for both 2x2 and 3x3 systems, I want to pause and discuss some common pitfalls. Even if you understand the theory, these small errors can quickly lead to the wrong answer. First, let's talk about sign errors when dealing with cofactors. When you are working on those larger 3x3 systems, like the factory example we just saw, it is incredibly easy to forget the alternating sign pattern. Remember, you must apply the pattern of plus minus plus in the first row, minus hyper minus in the second row, and plus minus plus in the third row. Forgetting to flip that sign for the middle elements is the most frequent mistake I see. Second, please be careful not to forget the transpose step. A very common mistake is to find the matrix of cofactors and stop there. But remember, to get the adjoint, you must transpose that cofactor matrix. You must turn your rows into columns. Always keep in mind that the adjoint of A equals the transpose of the cofactor matrix. Third, pay close attention to your multiplication order. In basic algebra, the order of multiplication doesn't matter, but in matrix algebra, it is not commutative. This means the order is critical. You must always calculate the inverse of a multiplied by B. Never, under any circumstances, calculate B multiplied by the inverse of A, as this will lead to an incorrect result. Finally, be extremely vigilant with your determinant calculation. As we saw in our examples, the determinant is the foundation of the entire process. If you make even a single small arithmetic error while calculating the determinant of A, it will cascade through your cofactor calculations, your adjoint, and your inverse, making your final solution completely wrong. My best advice is to always double-check your determinant calculation before moving forward. With these precautions in mind, let's wrap up with a quick summary of the key takeaways from this entire lesson. Key takeaways. To wrap up our session today, let's review the key takeaways to ensure you have a solid grasp of these methods before you move on to your practice problems. First, regarding 2x2 systems, remember that you don't need the long, complex process we used for larger matrices. You can use that handy shortcut for finding the inverse. Simply swap the elements on the main diagonal, change the signs of the off-diagonal elements, and then divide the entire matrix by the determinant. Second, when you are dealing with 3x3 systems, there is no shortcut. You must follow the more rigorous step-by-step path we practiced. Start by calculating the determinant of A, then find the matrix of cofactors. Move to the adjoint by transposing that matrix, calculate the inverse, and finally, arrive at your solution. Third, a very important point on consistency. Always check your determinant first. The matrix method only provides a single, unique solution if the determinant of A is not equal to 0. If the determinant is 0, the method won't work for finding a unique solution. Finally, never forget the fundamental final step. The solution for your variable matrix, x, is always found by multiplying the inverse of the coefficient matrix. A inverse by the constant matrix, b. In other words, x equals a inverse times b. Keep these points in mind, and you'll be well on your way to mastering systems of equations. Great job today!